Okay, so hi everyone, welcome. My name is Ke. I'm the executive co-director of PQI and the research faculty at the chemical engineering department here at Pitt. Welcome to the new Quantum 2020 PQI poster session. So for those of you who have attended our previous year's fall poster session, you may have noticed that the name is different this time. So we were part of the university-wide Science 2020 event, but that event was put on hold indefinitely. Therefore, starting this year, we're launching the new Quantum 2020 event, which will be held annually since this year, every fall. And we are very happy today to have 3 faculty judges and I think 1 student judges. Today, we have Professor Nathan Youngblood from Electrical and Computer Engineering Department at Pitt. We have Professor Qing Li from the Electrical and Computer Engineering Department at CMU. And we have Professor Patrick Irvin from the Physics Department here at Pitt. And we also have Emily Ike, who have won multiple poster awards with us. Yeah, hi, Emily, in the past years. And she's now a judge for this year. So welcome. And one note for the judges is that we will have this recording shared with you after this. So if you need additional time to finalize scores, you can do that and send it by Sunday night. And for the presenters, just a reminder that you will have 3 minutes to present and another 3 minutes to answer the questions from the judges. And I will give a note once you reach that time mark. But we have a relatively small group of presenters in this particular session, so I can be a little bit more lenient on the time, but still we would hope you can practice being concise. And another thing is please stay for the full hour to support and listen to your peers' presentation. And also, as you can see, the judges may not be from your area of expertise, which is by design. So please focus on making your presentation accessible to a broad audience. Okay, so without further ado, let's welcome our first presenter. Shiv, you're welcome to share, and the floor is yours.
Thank you. Okay. So you should be able to see my screen now. Okay.
Yep.
All right, so I'll go ahead and get started. What I'm going to be presenting on today is the role of high-order electron correlation effects in a model system for non-valence correlation-bound anions. And I'll get into exactly what that means in a second. First, I want to thank my collaborators, Amanda Dumi and James Shi, and my advisor, Kenneth Jordan, and PQI for the fellowship that supported part of this work. So the first thing is I'll be talking about anions, which are electronic systems where there's an excess electron, and these are, I'm talking about bound anions, which means the anion lies energetically below the neutral. And I have a depiction in the left side of the poster here. There's a couple of different ways you can look at this if you allow the geometry to relax. In this case, we're going to say that either the geometry relaxation is negligible or we're just looking at the vertical attachment energy. For these types of systems, that's equivalent. The model system we're going to be looking at is a water tetramer model system. So it's 4 waters arranged in a box like I've shown on the left side of the poster. And this undergoes a transition as we vary R. When R is larger than about 4.2 angstroms, we have a electrostatically bound system, which means in the Hartree-Fock, which is a mean field approximation, where you don't account for electron correlation, you're able to bind the electron. And methods that build upon that in a non-many body type of way are going to also be able to bind the electron. If you go smaller than 4.2 angstroms, you'll find that the mean field approach completely breaks down and you need to be dealing with electron correlation in a many body way. So we're going to focus on the region where correlation is extremely important. The many body method we're going to be using is diffusion Monte Carlo, which works in imaginary time to project out the ground state. And just briefly, since I'm already at 2 minutes, what we're looking at is if you go to imaginary time, all of your oscillating weights on your eigenfunctions become exponential decays if you're not at the ground state energy. So your ground state will exponentially grow, everything else will exponentially decay. If you introduced an energy shift, you can get it to the ground state will be normalized, so you wouldn't have exponential growth. DMC performs this in real space, and it was hard to imagine that this would work because your trial wave function is going to have collapsed onto the continuum, meaning the electron fell off. But what we're able to see in this table here is diffusion Monte Carlo is able to recover this binding, and it doesn't have a basis set dependence as other methods would have. All right, that's all I have to say. If there's any questions, I'd be happy to take them now.
Right on time. Any question from the judges?
Yeah, I have a question. So my understanding is that you used this method to do some calculation, right?
Yeah.
And the numbers are shown in your table, but how do you know that your calculation is correct, or this model is roughly, giving you the results you are expecting?
Yeah, so the important thing is we're able to find agreement between many different methods, and so I mean we can't perform something like a true ground state non-relativistic energy would be what we want, but we can't do full CI on this problem. So we can get close through something that builds upon like a wave function based approach, which would be this equation of motion coupled cluster. I don't have a lot of time to get into it, but it is like a many-body approach that develops in a different way than the diffusion Monte Carlo would develop. And then AFQMC works in a different space than DMC. So these three are all stochastic methods, and they agree with this deterministic method. And all three of those approach the many-body problem in slightly different ways. And so getting agreement between the methods is what really gives us some sort of certainty in our results.
Okay, thanks.
Mm-hmm.
I have a question too.
Yeah.
So I see here you're representing things as a tetramer, but I'm just curious, how well does a tetramer actually represent what happens in real world systems?
Yeah, that's a really good question. Okay, so this water tetramer would not occur in nature, because if you look at these hydrogens, all of the hydrogens are pointing towards each other. If we know anything about water, it likes a hydrogen bond. So this model is cut out of like larger water clusters. And so its only physicality in this sense is that it shows this transition between something that is a non-valence bound anion to a electrostatic anion. The physics is similar to actual molecules, but this wouldn't occur in nature. Other molecules that do occur, like if you take a benzene and change all of the hydrogens to fluorines, you get a really large quadrupole moment. And the physics between these two is similar, like you have a pretty large quadrupole moment here. And another system would be C60. The important part here is this system is small enough that we can treat it with really high accuracy methods. And once we find something that scales really well, like the stochastic methods I was just talking about, we would want to apply those to larger systems.
Okay, and then does that mean in this particular, in your calculations, you fix the geometry of the water so that the hydrogens are always pointing towards each other? Okay.
And the reason that is we get the dipole moments to cancel here, and we have a strong quadrupole moment. So what we're really doing is tuning the electrostatics of this system to act like something larger like C60. And so we're really just playing with the waters to approximate the physics of larger systems.
Got it. Cool. Thank you.
Yep. Thank you.
Thank you very much. In considering of time, we can move forward. Thank you, Shiv.
Yep. Thank you.
And the second presenter is Ryan.
Can you see my screen?
Yep.
Okay. Let me get my timer out. Okay, are we good? Okay, I'm gonna start now. Hello, my name is Ryan Muzzio. I work in the Department of Physics at Carnegie Mellon. And today I'm going to be presenting the work that I did under the guidance of Dr. Jody Katoch on the electrically tunable Van Hove singularities in twisted bilayer graphene. So ultimately, what we're looking at here is van der Waals heterostructures. And these van der Waals heterostructures, when you put them together, they're pretty weakly interacting with each other with respect to other conventionally grown materials, such as through like molecular beam epitaxy. And so what we can do is place them next to each other. I'm not allowed to zoom. Sorry, this requires me to zoom in for you all. And we're placing them on top of each other. And we're actually able to rotate them with respect to each other. So here I presented to you 2 layers of graphene. One is at 0 angle. Another is at 3 degrees and all the way up to 20. And you can see this, what we call a moire pattern forming. And these moire patterns actually allow you to create novel states because these moire patterns have nodes and antinodes that the electrons see, and therefore will form new states as if they're seeing a new lattice. And so the reason why we find these interesting is that in 2018, this group had taken 2 layers of graphene together at an angle of 1.1 degrees. And they found that these layers of graphene went into a superconducting state. And that is because there exists a weakly dispersing band, also known as a flat band, at the Fermi level. Now, what if we took 2 layers of graphene and made them, say, 12.2 degrees? And that's what we've done. And so we're interested in understanding the dynamics of that system. And so we utilize ARPES, which is a photoemission technique. So we are directly observing the momentum resolved band structure of these systems. And so here's a plot of that band structure where momentum is on the x-axis and energy is on the y-axis. And so here you can see 2 Dirac cones of graphene. And like I said, they're weakly interacting, so you can still see those Dirac cones pretty well. But what is really interesting is that you can see these weakly dispersing bands or flat bands that are occurring due to the interaction of the 2 here. So they actually are interacting, just like the 1 degree case. And the interesting thing is that not only do we just have 2 pieces of graphene sitting here, but we actually are able to probe them electrically. So we can drive current and we can apply a gate. And so when we apply the gate, what we notice is that the top layer of graphene, or twisted bilayer graphene, receives less electrons than the bottom layer, thus shifting the Dirac cones with respect to each other. That shifting, in turn, will then change the location of the flat band as well as the Van Hove singularity. So ultimately, what we're showing is direct evidence that not only does your angle give you a flat band at a certain energy, but also electrostatically doping it allows you to tune it. So this is the first direct observation of such things, which is important for transport and optical phenomena. Thank you.
Question from the judges?
Could you go over that last statement again? I didn't quite get what was the main conclusion there.
Yes, so the conclusion has 2 main parts to it. One, we knew already that if you change the twist angle with respect to the graphene sheets, just like I'm doing here on this slide here, you're going to change the moire periodicity, and you're also going to change where these flat bands exist. Something that had not been explored yet is the effect of gating on that system. And so when we apply the gate, we see that the interaction of the 2 Dirac cones changes as a function of gate voltage or carrier concentration, if you will. And so now we've opened up the parameter space of where these flat bands exist in energy. Not only do they depend on the rotation angle or the twist angle between the layers, but they also depend on the amount of electrons that exist in the relative layers.
And these flat bands are relevant because of superconducting properties?
So these flat bands, you can imagine that they have yes, they're pretty much theoretically they are shown to have extremely strong many-body interactions, and especially the electron-electron interactions. So they are a key component to superconductivity.
Can you clarify again what you're measuring when you're doing the electrostatic doping? What's being measured in that experiment?
Yes. So there's two parts. So the electrostatic doping is a really simple one. So first, we have a capacitor setup. So it's twisted bilayer graphene on one side of the capacitor and a graphite flake below it. And so when you apply a voltage between the two, you're essentially going to inject electrons or holes to one side and the opposite to the other. So that way we're able to control how many electrons exist in the twisted bilayer graphene. But then you're going to ask me, okay, so once you do that, what's happening? Well, we are shining photons onto our system. Excuse me, I'm going to go here. So we put photons down onto our system and they go under the process of photoemission. So they are ejected from our twisted bilayer graphene. After that, we capture them and we're able to calculate, knowing their angle of ejection and their energy, we're able to calculate what state they lived in the solid initially. And so that is what you're showing here is the truly momentum resolved view of the band structure. And so here's your momentum axis and here is your energy axis. Just like if you know about DFT and you calculate this, which you can see here, we directly measure it here. And from that direct measurement, we're able to find where these flat bands exist, as well as different other key features of the band structure.
So is this ARPES image at a one particular gate value?
So this is an ARPES image at no gate value. It's just a piece of twisted bilayer graphene with no gate applied. We took so many scans. There's a lot of scans here, but essentially every data point is its own scan here. So here you have the location in energy of the Van Hove singularity as a function of gate. And here you have the location of the flat band as a function of gate. And so effectively at a single gate voltage, you take a spectrum using ARPES, and then you can extract parameters like the Van Hove singularity and flat band as a function of carrier concentration or gate voltage.
Thank you.
Yeah, I have a very quick question. So how in the experiment, how do you control the angle? Like how do you know the angle of one graphene relative to the other? Like
So
can you see this structure?
So there's two ways that we try to do it. The first way that you can do it is by making your heterostructure in such a way. And there's plenty of ways you could try to do that, but I won't go into that. But let's just say you have a given heterostructure. Then you do photoemission on it, right? So we're given this picture. We can see the Dirac cones. So now we have a location in momentum of the Dirac points. You can then do a very simple calculation to go from momentum space to real space. And in that real space image, you can measure what the twist angle is.
Okay.
Very nice. Thank you very much.
Yeah, thank you all for listening.
The next presenter is Muquing.
So can everybody hear me?
Yeah.
Yeah, so today my talk is on nanoscale metal-to-insulator transition in a freestanding aluminate strontium titanate membrane. So LLSTO heterostructures bear many interesting properties, such as tunable superconductivity, tunable small orbit coupling, and magnetism. And in our group, we are particularly interested in the tunable metal-to-insulator transition at LLSTO interface. So when we have just under 4 unit cells of LEO grown on STO, the interface is intrinsically insulating. When we use a positively biased AFM tip to sketch on the LEO surface, the interface underneath it will become conducting. Meanwhile, a negatively biased AFM tip can restore the interface to an insulating state. So using this technique, we can create many interesting electronic devices such as single electron transistor, photon detectors, or electron waveguides. And in the meantime, we keep asking how we can integrate LUSTO to other materials to expand its utility, such as integration with flexible substrate or other low-dimensional materials or silicon architectures. So to realize this goal, we first think of directly growing LUSTO on other materials, but that is proven to be hard because of the chemical and structural mismatch. So here we use a method of chemical release. We sandwich a SRO layer between the LUSTO and the STO substrate. And by selective etching the SRO layer, we are able to release the LUSTO membrane, which is ready to be transferred on any other substrate. And in this picture, you can see we achieve millimeter-sized LUSTO membrane and with sharp interface and a single crystalline structure. And then after depositing gold titanium electrodes to contact the LUSTO interface, we perform the conductive FM lithography to create this 4-terminal nanowire device on this canvas. And as soon as the tip sketches the main channel with a positive voltage, you can see a conductance jump, and this jump can be erased with a negatively biased tip. So basically, we conclude that our LUSTO membrane has reconfigurable to the electron gas, and its conductance and the width of the nanowire are all comparable to the typical LU grown on bulk STO substrate. And this last part is to show that our nanowire is able to survive down to millikelvin temperatures, and at low temperature, it can show some superconducting feature, just like the bulk LUSTO. So in conclusion, we achieve a transferable and reconfigurable 2D electron gas at the LUSTO interface, ready to be transferred to other substrates. Thanks. Sorry, I'm finished. Thank you.
Thank you. Question from the judges?
Would you mind zooming into the top figure on the right-hand side?
You mean this one?
Yeah. So do you know what the source of that dip is?
So this dip, this blue curve is to show the nanowire width as a function of the tip voltage I used to create the nanowire. I don't think there's a monotonic behavior. It all ranges from 15 to 20 nanometer. That's what I wanted to show here.
Oh, okay. So what would the error bars be on those measurements? How do you measure the width?
So that's a good question. So the way I measure the width of the nanowire is I slowly cut this nanowire, and I record the change of the conductance, which is the red curve in this inset, and I feed this red decay of the conductance during the cutting, and I am able to get the nanowire width.
Oh, okay, okay. Thanks.
Thank you.
I have a question. So for your middle panel, is that a powder X-ray diffraction pattern you're showing on the bottom right there?
it's not a powder X-ray diffraction, it's X-ray diffraction on this membrane sample.
Okay, that's my question. Thank you.
Yeah, it's thin film, not powder. Yeah, thanks.
How many different substrates have you tried?
I've tried sapphire substrate and silicon substrate with patterned baggage, but this sample on sapphire works.
Okay, thank you very much.
Thanks.
The next presenter is Rodrigo.
Hi, can you see my screen?
Yep.
Okay, so yeah, first of all, good afternoon. My name is Rodrigo, and I'm a first-year student at Pitt. And today I'll be presenting about Tubularenes, which is a new class of tubular organic frameworks. And what characterizes this class is the fact that they are very highly strained aromatic frameworks with a tubular shape. And the first were developed in the Hernandez Sanchez group. And they are very exciting because of potential applications due to the fact that their architectures are very versatile, modular, and tunable. So in this work, we have tried to synthesize a specific tubularene. So in this figure, we see the structure and the molecular model of that tubularene that we have been working on. So as you can see, it is mainly composed of perilene-based walls with a resorcinarene-based molecular cap on the bottom region of the structure. However, one of the main challenges that we have with developing such structures is the synthesis. So in order to solve this challenge, we have adopted that synthetic approach, in which we start with these two reactants. The first one to compose the walls of the tubularenes, and the second one to compose the basal structure. So to synthesize the first one, we started from perilene tetracarboxylic dianhydride, which is commercially available. And after performing these two reactions, we managed to halogenate the compound. And in order to obtain the pure regioisomerically form that we wanted, we had to recrystallize. And finally, we managed to form the anhydride in one of the sides by adding heptane. And after that, we also had to synthesize the second reactant. And to do so, we adopted a scaffold approach, in which we started with the resorcinarene-based compound, which would compose the bottom of the tubularene. And to that, we managed to, we will add nitro or bromobenzene in order to obtain this one or that one, followed by reduction or substitution in order to obtain the final reactant we want. And our hope is that we will be able to synthesize the final structure and the final compound that we are desiring. And with future studies on the mechanical, electrical, and the structural properties, potential applications could be developed. And the reason why these kind of structures are so relevant is because of the potential for tuning those structures according to specific properties. And so that's pretty much it. And I would like to thank you for listening. And if you have any questions, let me know.
So you mentioned tuning the structures to reach like desired properties. What would you be tuning?
Yes. So thank you for the question, first of all. So for example, let me show the structure here. So if we look at the bottom part of the structure, we see that we have some alkyl chains with 5 carbons, as well as some alkyl chains on the top part of the structure. So we are able to, for example, change the length of those chains by using C11 or like under-seal chains or dual-seal chains. And by doing so, we are able to change the solubility. So if you want a more soluble structure, depending on the application, if it's for drug delivery or like any application, like we can change those alkyl chains. Another way to tune those structures is, for example, playing with the internal void that we have, because if we see from the top, those structures, it's essentially a void that we have, like a capsule. And if we can play with the structures of the walls, of the substituents on the walls, we can also fine tune the diameter of the structures and so on.
I see. Thank you. Okay.
I have a quick question.
Yes.
So going off of that, I'm just curious. So here you say you want to characterize the structure after you synthesize the final tubularene. And so I'm sort of making analogies to like metal organic frameworks. So are you interested in like doing TGA analysis and things like that? Could you just expand upon what you mean by structural characterization?
Yes, so in regards to the structure characterization, X-ray diffraction can be done, and like TGA analysis, like DSC, all the typical characterizations. Also, to analyze because one of the main features of this structure is the presence of high permanent porosity, which could potentially be used as a gas adsorption sensor, for example. So one of the ways of characterizing that compound could be like adsorption, like hydrogen adsorption characterization.
Thank you.
Thank you.
Okay, if there are no further questions, thank you, Rodrigo. And since I don't think we have our last presenter, so it seems the next presentation will be the last one in this session, and it will be Danielle. Welcome.
Thank you. Okay. Okay, great. All right, thank you. My name is Danielle. I work in the Hutchison Research Group in the Department of Chemistry at Pitt. And today I'm going to be talking about the Pareto optimization of polymer polarizability and dipole moment using a genetic algorithm. So a little bit about the motivation for this project. So we're looking for novel polymer structures that have large dielectric constants because these would be super useful for a variety of energy-related applications and specifically high-efficiency capacitors. So previously in the group, we used the Debye equation to relate the dielectric constant to the molecular properties of polarizability and dipole moment, which you can see here are the two terms on the right-hand side. So we calculated these properties and then therefore their terms for the entire 3 million plus molecules in the PubChem QC dataset. Just to get a feel for what was already out there. And we noticed that there was this seeming trade-off between these two terms, at least for this data set, and that appeared to be perhaps a Pareto front where it was difficult to find any species up in this area where both the polarizability and dipole moment terms are both maximized, which would then of course maximize the dielectric constant. So the main question for this project was how rigid is this apparent trade-off, specifically in the realm of polymers? Can we break through it? What kind of molecules can we find up here? So the way that we did this was using a genetic algorithm, which is a computational technique. Basically, in our case, we created sets of hexamers from a set of small conjugated monomers. And then we ran through the 3 steps of the genetic algorithm, which are borrowed from Darwinian evolution. So in the first step, the selection step, we choose the best polymers that we found so far based on the criteria, in this case, both polarizability and dipole moment terms. Then we do a crossover step where we take our good solutions to this optimization problem and combine their features to create new, hopefully even better solutions. And then finally, we go through a mutation step where we randomly select certain polymers to have certain features changed, such as changing one or more monomer species or changing their sequences. And then we repeat this cycle for a set number of times until hopefully we find polymers that have been optimized for our criteria. So looking at our actual data, we did 3 runs, each run was run for 400 cycles of that genetic algorithm. And then each run also, all of the polymers had the same sets of N groups to see if there was any difference there. We didn't see any major differences using different sets of N groups. Well, you can see what we did do was we managed to break through that perceived Pareto front, at least for these sets of polymers, where we were finding polymers here that had maximized both the polarizability and dipole moment terms. In order to perform analysis, we divided these plots into 6 equally sized bins based on the median polarizability term value and then thirds between the smallest and largest dipole term values. So then we focused our analysis on the third bin, where we found that 2 major conclusions were that the sequences tend to be segregated such that all of one monomer were on one side, all of the other monomer were on the other side, and that among these top candidates, they generally had 2 types of monomers, one that was primarily electron donating and one that was primarily electron accepting. Thank you.
Thank you. Question from judges?
I might have missed this, but was there a specific physical intuition as to why there's this trade-off that you see?
So that's something that that's basically what we wanted to explore. We weren't sure if, in terms of hypothesizing about why this could have been, would be that the permanent dipole moment and the overall polarizability of the molecule are working against each other, essentially. That if you have the ability to have a lot of charge transfer for a larger polarizability, that perhaps that inhibits there being a permanent dipole moment, but that would be a hypothesis. So we wanted to test, I guess in this case, we wanted to test whether that was actually true and held true for the set of polymers, which we found that it did not necessarily hold true.
Okay, thanks.
Are all of the polymers that the genetic algorithm comes up with, are they always synthesizable?
So we believe them to be synthesizable. So the way that we create them is from a preformed list of either already synthesized small organic monomers or obvious synthetic derivations thereof. And then the way that we put them together would be in such a way that we believe the connection points, et cetera, would be able to be synthesized in the lab.
Can I ask you a quick question?
Sure, go ahead.
Are you plotting, is that the isotropic polarizability? So like the traces?
Yes.
Yeah, okay. And
yes.
whenever you find those top candidates, is it like, do they have like a particular like is alpha ZZ really big, or is it just like all of the values have gotten really big in the polarizability?
That's actually a really good question. That's something, so I'm currently looking at the individual tensor elements, so I don't actually know if there's a trend there, but that is a really good question. So yeah, so far we basically only looked at the isotropic polarizabilities because that's what we're using for ranking. So yeah.
That makes sense. Thank you.
Mm-hmm.
So this crossover step in your algorithm, right?
Yes.
What is the physical meaning of that?
Right. So basically, so the crossover step is to do kind of a depth search in terms of how we're doing the optimization process. So in the selection step, I generally keep half of each generation of polymers. So I take that top half and then I take 2 of the polymers and then combine features. So in this specific case, what I'm actually combining would be the sequence from one of the 2 polymers and then the monomers from one or both of the polymers to create a new polymer, if that makes sense. So essentially, we're trying to look at the features of monomer species and sequence in good solutions to the optimization problem to potentially come up with a better solution.
Okay, thanks.
Okay, thank you.
Thank
And
you
if there are no further questions, thanks to all the judges and students who stick around. We have a shorter session today, and that concludes our session. Thank you for coming. Yeah.
Thank you.
Thanks.
Thank you.
Bye. Thanks.